I'm going to talk about trigonometric identities, including the sum and difference identities. Okay? Now, first, let me make it clear what I mean by an identity. Okay? Identities look like equations, but they serve a different purpose. Identities are used to state equivalent expressions. Okay, why would you care about equivalent expressions? Well, you can have a complicated expression, and if it's equivalent to a simpler expression, I would guess that you might choose to work with the simpler expression instead, right? Okay? So here are some examples of identities. Okay? So it's clear that in the first identity that the left side is more complicated than the right side. Everywhere in an equation that you see the left side of the first identity, you can replace it with the right identity. Do you see that you wouldn't really solve that first identity for x? That's not the purpose of that identity. The second one, you might prefer the absolute value version, or if you don't like absolute values, you can replace an absolute value with the left side, the square root of x squared. Okay, they're both equivalent. You can replace one with the other. And then identities aren't just limited to one variable. So the last example is an example of an identity with two variables. The left and right sides, again, are interchangeable. All right? Now I'm going to discuss some very important trigonometric identities. I'm first going to write them down, and then I'm going to show you where they come from. All right? So here are what's referred to as the sum and difference identities. All right, let me stop there for a minute. So I actually wrote, that actually represents two identities, okay? There's a plus version and a minus version. That's what the plus or minus does for us. It allows us to represent two identities, okay, without having to take up so much room. Okay, and then there's a cosine identity. Now, notice that on the right side, I have the plus below the minus. What that represents is that the sign of the right side is going to be different than the sign of the left side. For example, if on the left side I have the cosine of alpha plus beta, then the right side will be a difference. If on the left side I have the cosine of alpha minus beta, then on the right side I'll have a sum. And then lastly, there's two identities with respect to the tangent function. And so please make a note of those. Notice that in the denominator of the last identity that I have a plus below the minus. So that means that if there's a sum in the numerator, I'll have a difference in the denominator. If I have a difference in the numerator, I'll have a sum in the denominator, right? Okay, so let me now show you where these identities come from. Okay, this is going to be my strategy to show you where the identities come from. First, I'm going to just assume the cosine sum identity. And I'm going to show you that all the other identities follow from this one identity. Okay? After I've convinced you that this identity is the only assumption, then I'll show you where this one identity that we had to assume comes from. Okay? So let's first get the difference identity with respect to cosine. So for the difference, I need to realize that I can write the difference in terms of a sum, right? Alpha plus the negation of b, okay? And so that's equal to the cosine of alpha. And then if I take the cosine of negative beta, that's equivalent to the cosine of beta. Now that's not true with respect to the sine function. The sine of negative beta is actually minus the sine of beta, so that's going to end up changing that minus to a plus. Okay, and so there you have it. There's the difference identity for cosine. All right, now let's see if we can get the sine identities. So we need to utilize the fact that the sine of an angle is equal to the cosine of that angle's complement. So the sine of alpha plus beta is equal to the cosine of the complement of the angle with a measure of alpha plus beta. So cosine of pi over 2 minus alpha plus beta. Okay? And that's equal to, rearranging, we have the cosine of pi over 2 minus alpha minus beta. Okay? And so let's now use the difference identity with respect to cosine on what I have on the right side there. So I will get the cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. All right, but didn't we just finish saying that the cosine of an angle is the sine of its complement and vice versa? So I can rewrite what I have so far as the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. All right? And then to get the difference formula, I can do something similar to what I did to get the difference identity. I can use something similar to what I did to get the difference identity for cosine. So let's go ahead and do that. The sine of alpha minus beta. And so I'm going to interpret that as I'm going to interpret alpha minus beta as a sum, alpha plus the negation of beta. Okay, so let me in the last right side of what I just wrote down, let me replace beta with minus beta. So that's not going to change the cosine, so I'll just keep that cosine of beta. But on the next term, the sine of minus beta, that's equal to minus the sine of beta. Okay, so that gets me the sine and cosine sum and difference identities. Okay, now what about the tangent identities? All right, let's work on those next. So the tangent of alpha plus beta. So first of all, would you agree that that's equal to the sine of alpha plus beta over the cosine of alpha plus beta? Okay, so let's write out what the numerator and denominator are equal to. So the numerator is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. And the denominator is equal to cosine alpha cosine beta minus the sine of alpha times the sine of beta. Okay, now we need to somehow turn all the trig functions into numbers or tangents. So let's do this. Let me divide everything by the product of the cosine of alpha and the cosine of beta. So I'm going to multiply the top by 1 over cosine alpha cosine beta, and I'm going to multiply the bottom by 1 over cosine alpha cosine of beta. Let me clean up my writing here first. Cosine alpha cosine of beta, cosine alpha cosine of beta. Okay, so the first term in the numerator becomes, let's see, after the cancellation I have a tangent of alpha, and then the second term in the numerator after the cancellation I have tangent of beta, and then in the denominator, the first term after the cancellation I have I have a 1. And then the last term in the denominator, I have a minus product of tangents, minus tangent alpha, tangent of beta. And then to get the tangent of alpha minus beta, I'm going to use the right side that I just wrote down, and I'm going to replace beta with minus beta, because I'm going to interpret alpha minus beta again as a sum, alpha plus the negation of beta. So let's see, in the numerator what happens, how is the tangent of minus beta related to the tangent of beta? Well, they differ by a sine. And then let's see what happens in the denominator. So again, they differ by a sign, the tangent of beta and tangent of minus beta, so that's going to change the minus to a plus. Okay, and so there you go. I've derived all the identities from the sum identity for the cosine. Now, you don't need to know how to derive these. This is just for your benefit if you're interested. Now, I'm going to show you now how to derive the cosine of alpha plus beta identity. Okay, and again, this will take a few steps, and again, it's not required, but I would still encourage you to follow along if you can. Okay, give me a minute to make a picture. Okay, so I've drawn an angle with a measure alpha, and I've drawn an angle with a measure beta. I've drawn a line segment with a length 1, and then I've drawn other line segments that are perpendicular to various line segments in the picture. Okay? So this picture is going to help us to derive the sum identity for cosine. Now, in order for you to follow along, you need to know that the cosine of an angle, of an acute angle inside of a right triangle, is equal to the ratio of the side length adjacent to that angle divided by the length of the hypotenuse. Okay? If you know that about cosines, that's all you need to follow along. Okay, so notice that the line segment with a length of 1, notice that that is the hypotenuse of a right triangle. It's the hypotenuse of a right triangle with an angle of measure beta. Okay, therefore, one of those legs has a length cosine beta. Okay, the other leg of that same right triangle has a length sine beta. Okay, also notice that the two angles with measures alpha and beta, together they form a bigger angle with a measure of alpha plus beta. And that combination is itself the angle of a right triangle. The right triangle that has a hypotenuse of length 1. So all of that is to say that I know the length of the legs of that right triangle. So the cosine of alpha plus beta. Okay? And now notice that at the bottom, towards the bottom of the picture, I keep focusing on different right triangles. Now I'm going to focus on the right triangle towards the bottom of the picture with the hypotenuse of length cosine of beta. Okay? That has an angle of measure alpha. So the horizontal leg of that right triangle that I'm focusing on goes from one end of the picture to the other. So let me identify the length I'm talking about. Okay, now again, that is the leg of the right triangle with a hypotenuse of length cosine of beta. and that leg is adjacent to the angle with a measure alpha. So all of that is to say that the length of that side is the hypotenuse length times the cosine of alpha. Okay? Now I need to identify some angles before I identify the length of the last length that I need. Okay? So look at the angle with a measure alpha for a minute. Okay? Can you see that that implies that this little angle right here also has a measure alpha? If you know about parallel lines cut by a transversal, and if you remember alternate interior angles, that's one way to see that that angle must also be alpha. Okay? Another way to see it is that this angle right here is 90 degrees minus alpha. Okay, so the other angle is its complement. The complement of an angle with a measure of 90 degrees minus alpha is alpha. Okay, so either way, I hope you can see that that angle there, that little angle, has a measure alpha. Okay, now the complement of that angle has to have, in other words, this right here, this is the complement of that angle. That has to have a measure 90 degrees minus alpha. And then the complement of that angle has to have measure alpha, which means that this one up here has to have a measure alpha. Okay, so I used a few different complementary angle pairs to get to the fact that that angle at the top there has to have a measure alpha. So you might want to pause the video and go through that slowly if you didn't quite see all that the first time. Okay, so now I'd like to focus on the right triangle in the upper right that has a hypotenuse of length sine of beta and an angle of measure alpha. So the side opposite to the angle alpha has the one down here. That one has a length equal to the length of the hypotenuse times the sine of alpha. All right, we finally have enough information that we can derive the identity that was our original goal. Okay, now the length that I've written in green there at the bottom, can you see that if I subtract the last length I determined, sine beta, sine alpha, if I subtract sine beta, sine alpha from that green length, I get the cosine of alpha plus beta? Okay, so let me write that. If I take that green length and I subtract that the last length that I just determined, then what's left when I subtract those two lengths? I get that length there at the bottom in purple, cosine of alpha plus beta. Okay, so there you have it. We just showed that the cosine of alpha plus beta is equal to the cosine of beta times the cosine of alpha minus the sine of beta times the sine of alpha. Okay? So now that we've shown where those identities come from, let's actually do some exercises that use, once we've accepted those identities, that actually use those identities. Let me show you how to use the identities we just determined to find the sine of 15 degrees. So 15 degrees is not one of our special angle measures. However, we can express it as the difference of some of our special angle measures. Okay, so now we can use the identity, the difference identity for sine to make progress. So that's going to give the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. And that's going to equal root 2 over 2 times the cosine of 30, which is root 3 over 2, minus cosine of 45 degrees is root 2 over 2. Sine of 30 degrees is 1/2. So this simplifies to root 6 over 4 minus root 2 over 4. Packaging it all up, root 6 minus root 2 over 4. Okay? Now, I'd like you to try your hand at a similar problem. Can you please try to find the cosine of 75 degrees without a calculator? Okay? Pause the video and try that now, please. All right, I'll go ahead and work it out as well. So it's equal to the cosine of 45 degrees plus 30 degrees. So now we use the sum identity with respect to cosine, and we'll get the cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 degrees times the sine of 30 degrees. Now we evaluate all of those trig functions, so we get root 2 over 2 times the cosine of 30, which is equal to root 3 over 2, minus root 2 over 2 times the sine of 30, which is 1/2. So root 6 over 4 minus root 2 over 4, packaging it all up. Notice we got the same answer we did on the last problem. Okay, the reason we got the same answer we did on the last problem is because 15 degrees plus 75 degrees add up to 90 degrees. Okay? Now, would you please do one more example? Try to find the tangent of 105 degrees without a calculator. Pause the video and do that now if you like. Okay, so I'll go ahead and work this one out as well. The tangent of 60 degrees plus 45 degrees, and using the sum identity with respect to tangent, we get the tangent of 60 degrees plus the tangent of 45 degrees divided by 1 minus the tangent of 60 degrees times the tangent of 45 degrees. And let's see what we can do with that. So the tangent of 45 degrees is 1. We like that. And the tangent of 60 degrees is the sine of 60 degrees divided by the cosine of 60 degrees. Sine of 60 degrees is root 3 over 2. Divide that by half, so we get root 3 for the tangent of 60. All right, so this is equal to, let's see, 1 plus the square root of 3 on top, 1 minus the square root of 3 on bottom. Now, maybe I can, just to be fancy, remove the radical from the bottom, although that's not strictly necessary. I'll multiply the top and bottom by 1 plus the square root of 3. So on top, I will get 1 plus 3 plus 2 root 3, and on bottom I will get 1 minus 3. So all that gives 4 plus 2 root 3 divided by minus 2. That all gives minus 2 minus root 3, which actually does look a lot simpler, so that was actually not a bad idea. All right.